I also would like to express my gratitude for being able to be here these days. I've learned a great deal about what the kind of science that James Webb does and how it's changing the world. So thank you very much. I'll be talking about the giant planets in our solar system. That's Jupiter, Saturn, Uranus, and Neptune. But I'm not. I'm just talking about Uranus and Neptune because I think that's where the gold dust is in these initial, not literally, but that's where the good stuff is initially anyway. So I'm going to show you this picture, which Stephanie showed as well. A really marvelous overview of a giant planet system. We have the rings, of course. We have the belts and zones of Jupiter, the atmospheric turbulence. Jupiter is very big. You see the great red spot right there. The largest storm in the solar system. Storm was there when Galileo looked at the planet. You can fit the entirety of the Earth inside that storm, right? It's a pretty big planet. A day on Jupiter is only 10 hours long, and that creates this incredibly turbulent atmosphere, which you can see in the grays and the blues on the disk. Actually, the grays and whatever, yellows. The blue is what I'm interested in. The blue is emission from the very top of the atmosphere, the upper atmosphere, and more specifically is the ionosphere, so the charged particle component sitting at the very top of the atmosphere. You can see there's blues all the way across the disk of Jupiter, from the equator, where the ionosphere is produced by solar EUV ionization, so the sun is ionizing the atomic and molecular hydrogen in the upper atmosphere. At the poles, He+ is formed, I haven't talked about He+ yet, but the ionosphere is formed via electron impact ionization. So plasma is charging down magnetic field lines, impacting the upper atmosphere, producing ionization. This molecular ion, He+, trihydrogen cation, is one of the most dominant ions in Jupiter's ionosphere. And it's one of the most important tools we have in our arsenal in trying to understand how the upper atmosphere works, how it couples to the space environment, and how it couples to the layers below it. For example, the stormy atmosphere you see here. So you can pose a very simple question here. Where do these charged particles come from that generate the aurora, right? So for the Earth, it's well established that the charged particles that generate the northern and southern lights, the aurora at the Earth, come from the sun. You know, our experience of the sun on a day-to-day level is not that it's very active, but it throws out a lot of material all the time, and these are charged particles in form of plasma, and we call this the solar wind. Solar wind gets trapped, particles get trapped in our magnetic field, and it gets funneled down to produce the aurora. Now, Jupiter is fundamentally different. Jupiter has this internal source of plasma, which is Moon Io. It's one of the most volcanic places in the solar system. And you can see a movie there on the right, taken by the New Horizons spacecraft as they flew by Jupiter on the way to Pluto. You can see these volcanoes literally spewing out material into the volume around Jupiter. This material gets charged and converted into plasma, and is that generates the really bright northern lights at Jupiter. So Jupiter is fundamentally different from the Earth in this respect. A bigger point you can say here is that by looking at auroral emissions at these planets, you can actually infer the presence of geologically active moons within these systems. It's quite a powerful tool. Okay, so here's the spectra we have of the giant planets to date with the NIRSpec IFU and MIRI MRS. Jupiter is by far the brightest of them, and in fact, it's a little bit too bright. We do saturate a little bit, so we have to go down to one group if possible, and still possibly saturating in that case. Saturn, we don't have any NIRSpec data yet for Saturn. That might change today or tomorrow, whenever it is, we'll see. But what's really interesting here is that we'll look at just in terms of brightness, is that Uranus and Neptune are really dark compared to Jupiter and Saturn. And if you want to look at really new discovery science in this James Webb data, you look at the regions at Uranus and Neptune where they are dark themselves. And it turns out the ionosphere, H2 plus ionosphere, is one of those things. We've never seen H2 plus at Neptune, ever. And I've been trying. I've been nights up mountains staring at Neptune, not being able to see it. It's really weak from Uranus. So it's a good place to start when looking at this James Webb data we have. So I just want to give you a little bit about background about these two planets before I start delving into the James Webb data. So Uranus and Neptune are quite strange worlds. Uranus is, of course, tilted on its side. It rotates. Spin axis is in the field, in the plane of the ecliptic, essentially. The magnetic field is offset 60 degrees from that. The whole system spins around every day. So if you're looking for northern lights at Uranus, you should be looking at the equator, not the poles. They also have very complicated fields. So it's not just dipole fields. They have complicated quadrupole and octopole magnetic field components. Creates a very complicated environment, interaction with the space environment. And of course, they receive very little sunlight as well. So on the right, you have a very simple schematic of the chemistry in the upper atmosphere of these planets. We have atomic and molecular hydrogen, that's the main constituents. We throw some sort of energy into the system, that's either solar EUV photons or energetic electrons. You can do one of two things, right? You can excite the constituents of the atmosphere, that creates emissions in the ultraviolet, you can see with Hubble, or you can ionize the constituents of the atmosphere, and that creates H3+. We can see in the near infrared, that's IRTF, Hawaii, or of course, the James Webb Space Telescope. So these are the tools we use to study the upper atmosphere. What we know about Uranus and Neptune, really most of it comes from the Voyager 2 flyby. The Voyager 2 flew by Uranus in 1986, Neptune in 1989. So this is, top-notch 1970s technology as well. So what I'm showing here is maps of auroral emissions at Uranus. This is latitude as a function of longitude, and where it's bright, that's where the auroral emissions are. You can see for Uranus, the aurora does appear close to the equator. And for Neptune, you don't see these kind of maps anymore. They've gone out of fashion. But there is a hint of aurora in the southern hemisphere. Here, south is away from you for some reason. Another important result that Voyager 2 did is that these planets are really hot. The upper atmosphere is surprisingly hot, 750 Kelvin. These planets receive very little sunlight, and that's still an open question. Why are the upper atmospheres of the giant planets so incredibly hot? We'll come back to that. Just briefly, we have been able to observe the northern lights and southern lights of these planets, certainly Uranus with the Hubble Space Telescope, but these are extremely challenging observations. So if we look at Uranus, there are some helpful arrows, sort of it's a 1 sigma detection of some auroral emissions. It's not great. For Neptune, we've never seen any hint of auroral emissions with Hubble. So we need a better tool, and that better tool is the James Webb Space Telescope. So we'll have two sets of observation of Uranus, Uranus and Neptune. So these are GTO observations led by Lee Fletcher. The GTO time awarded to Heidi and run by Stephanie as well. So we have 3 longitudes. So what I'm showing here is just maps of clouds. So just like the inclement weather they had this morning, this is just clouds on Neptune and Uranus. So Uranus is at the top. We have 3 longitudes separated by 120 degrees rotation. So this gives us essentially global coverage of the whole sort of surface of the planet. For Neptune, we have 2 longitudes separated by 180 degrees. Gives us pretty good global coverage. So in this wavelength, IFU wavelength range, we do have lots of H2+ lines, and that means we can determine the auroral morphology, and we can determine through spectral fitting, we can get the temperature, and ion densities, and all that really fun stuff. So I'll start with Uranus. So top left, top right even, we have the median spectrum of Uranus, all these 3 longitudes, and this is an extraordinary spectrum. So there's a red line, which is the model, and you can barely see the data underneath it, right? The spectral fit is amazing. And so we get a temperature of 413 Kelvin, plus or minus basically 1 Kelvin. Amazing data, but we know that. This temperature is actually the coldest temperature we've ever observed in the upper atmosphere of Uranus. And this fits in with a long-term trend that I've been working on for a decade or so. Ever since H2 Plus was discovered at Uranus in 1992, the temperature has been steadily dropping over the decade. And this coldest temperature from James Webb sort of fits in with that large picture. So this is really surprising. It means essentially that the upper atmosphere at one solstice was really hot. We're moving to the other solstice in 2028, and it's going to be really cold. This is some really weird seasonal behavior that we don't fully understand yet, but it's certainly, you know, a fun thing to, you know, investigate. You can map the H2 Plus emissions. So here at the top, I'm showing just clouds again at low altitude. And at the bottom, I'm showing H2 Plus emission right in the upper atmosphere. And you can see there is a large emission. So the whole disk basically glows in H2 Plus. And this is the component produced by the solar EUV. But you can also see some dots on there. And these are the northern and southern lights of Uranus properly resolved in the infrared for the very first time. I can show another view of this. So here, imagine you're looking above, you're standing, hovering somewhere above the North Pole of Uranus, and you're just looking down. So the geometry changes as the planet rotates. So you can see the northern and southern lights it should appear close to those contours. That's basically the magnetic field model, and they do, and there is some variability there. There's another surprise in here, which was completely unexpected. And if you look right at the center of the disk, help your eyeballs, there is sort of a V shape. There's a dark V shape in the ionosphere right at the pole. And what is this? Well, at Jupiter, at the magnetic equator, there is a dark ribbon that basically follows it. Could the same thing be happening at Uranus? Yeah, perhaps. Uranus has an extremely complicated magnetic field, dipoles, quadrupoles, octopoles. You get very complicated magnetic equators, for example. So we could potentially refine the magnetic field models at Uranus before we even fly a mission there. Okay, this is the most important part of this talk, and we've all had, it sounds like days that are totally amazing when you get the data down from the Mars servers and you get to play with it for the first time. And you see things that you were really only dreaming of to see, right? And here we have the first detection of H2 Plus at Neptune. And this is I'm really excited about this. This is my favorite result ever. So with basically one shot of James Webb observations, we do detect H2 Plus at Neptune for the very first time. We can fit a model to it, which is at the bottom, some background subtractions, etc. We can fit a temperature as well. And this is surprising. We get a temperature of the upper atmosphere that's 358 Kelvin. Voyager 2 derives 750 Kelvin. So that's more than half of what Voyager 2 is. So we saw previously that Uranus has been cooling on a timescale of decades. What's happening at Neptune? What are the chances that Neptune should also cool at the same time, similar sort of rate? So we need more observations to really understand what's happening here. I know I'm out of time. I also want to show you, we can map out the emissions of Neptune. And at the bottom right, we do see a bright patch of emission. And we can map this to latitude and longitude, and that agrees with the magnetic field models, the expected location of the southern lights of Neptune. Not only do we detect H2 Plus for the very first time, we also detect the southern aurora of Neptune for the very first time. And this really opens doors to understanding how Neptune interacts with the surrounding space environment and how the upper atmosphere acts as a conduit, energy exchange between these systems. So I'm just going to leave that up there.